Welcome to the Explainer. If you've ever stared at a squiggly wave on a graph or a messy jumble of sines and cosines and just thought, nope, well, you're in exactly the right place. Today, we're taking all that abstract math and turning it into clear, visual, and highly logical steps to help you absolutely crush your IGCSE exams.
Today, we're tackling three main things: visualizing the wave with graphs, mastering the rulebook of identities, and finally, solving the puzzle of complex equations. Let's get right into it.
Act 1. Visualizing the wave, focusing on graphs.
Now, your syllabus technically covers 6 trigonometric functions. So we've got sine, cosine, tangent, plus their reciprocals, secant, cosecant, and cotangent. But let's ground ourselves with the big 3. You'll notice sine and cosine are kind of like well-behaved twins. They have very strict boundaries, bouncing between positive and negative 1. But tangent? Tangent is the absolute wild child, just stretching from negative infinity all the way up to positive infinity.
Okay, let's unpack a little bit of jargon. Amplitude. Honestly, just think of this as the height of your wave from its flat resting center line. For a standard sine or cosine wave, that amplitude is exactly 1. And hey, this perfectly explains why tangent doesn't even have an amplitude. I mean, you literally can't measure a maximum height when the wave shoots straight off the page into infinity, right?
Then we have the natural period. This is just the length of a single complete cycle before the wave copy-pastes itself and starts all over again. For sine and cosine, that cycle takes a full, leisurely 360 degrees. But tangent? It moves way faster, wrapping up its whole cycle in a much tighter 180 degrees.
Ever plugged tangent and 90 into your calculator and gotten that annoying math error? Well, visually, that error is an asymptote. Basically, it's an invisible, infinite boundary line. For a standard tan graph, these hit at exactly 90 and 270 degrees. The curve will sneak closer and closer to these dotted lines, stretching up to infinity, but it mathematically cannot ever touch or cross them. Which is kind of mind-blowing when you think about it.
So, what happens when we start messing with the equations? Take something like y equals 3 sine 2x minus 1. Every single number here just tweaks the original baseline shape. That 3 in the front, that's your a value. It stretches the amplitude, making the waves 3 times taller. The 2 right next to the x, that's b. It squishes the wave horizontally, so your new period is 360 divided by 2, giving us 180 degrees. And that minus 1 hanging off the end, that's c, and it literally just steps the entire wave down by 1 unit on the y-axis.
Moving right along to Act 2, the rulebook, where we tackle identities. These are your absolute mathematical truths. An identity isn't just something you solve, it's a fact that holds true for any angle you throw at it. The absolute heavy hitter is the Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. But remember, your syllabus takes this further. By dividing this core equation, you unlock 2 more absolute must-knows. Secant squared theta equals 1 plus tangent squared theta, and cosecant squared theta equals 1 plus cotangent theta. These formulas are basically your skeleton key for unlocking complex proofs.
When you're asked to prove an identity, I want you to use a goal-to-method framework. Instead of just staring blankly at a tangled mess of trig functions, zero in on your target, what you actually want the equation to look like at the end. For instance, if your target side is completely made of cosines, well, your goal is obvious. Grab your identity rulebook and ruthlessly swap out any tangents or sines until only cosines are left. Having a step-by-step strategy here is a total game changer, keeping you from getting bogged down. Rule number 1, completely ignore the right side of the equation at first. Just work on expanding the left. Swap out tricky terms, like turning a tangent squared into sine squared over cosine squared. Combine your fractions, look for common terms, and when you spot something like sine squared minus cosine squared, boom, sub in a Pythagorean identity, simplify it down, and suddenly you match the right side perfectly. QED, proof is done.
Now, proving these absolute truths feels pretty great, but what happens when we shift gears from proving rules to hunting down missing numbers? Specifically, what on earth do you do when your equation spits out a negative ratio?
That brings us to Act 3, the puzzle, where we solve equations within a strict domain.
Okay, here is the absolute golden rule of solving trigonometric equations. Before you even think about dealing with negative numbers, you have to find your base answer. Say your equation is sine of x equals negative 0.68. I want you to completely ignore that minus sign for a second. Just punch the inverse sine of positive 0.68 into your calculator. That gives you an acute angle, and that right there is your anchor point. Once you have that anchor, we bring out the cast diagram.
The memory trick add sugar to coffee is a lifesaver here. It tells us exactly which trig functions are positive in which of the 4 quadrants. So if we go back to our negative sine value, we look at the diagram. Sine is positive in the first 2 quadrants, which means it has to be negative in quadrants 3 and 4. So we just take that positive base angle we anchored earlier and map it into those bottom 2 quadrants by adding it to 180 and subtracting it from 360.
Let's apply this to something that looks a bit scary, like a quadratic trig equation. The trick is to break it down into repeatable steps. If you have 5 sine squared x minus 2 sine x equals 0, just factor out the common sine x, exactly like you would if it was just a regular algebra problem with an x. Instantly, this splits your clunky equation into 2 totally manageable pieces. You find your base angle for each piece, run them through the cast diagram, and boom, you've unearthed all the possible solutions in the 360-degree cycle.
Of course, sometimes the puzzle tries to throw you a curveball by mixing up the functions. If you're staring at an equation where a sine and a cosine are hanging out together and the whole thing equals 0, there's a brilliant magic trick. Just divide the entire equation by cosine. The sine divided by cosine transforms into a tangent. The cosines cancel each other out completely, and just like that, you're left with a clean single-function tangent equation that is totally solvable.
And there you have it. You've got the exact framework to visualize the graphs, master complex identities, and solve whatever mathematical puzzle the IGCSE syllabus tries to throw your way.